Hello everyone, this is a great pleasure to be here to introduce to you the paper which is called Semi-Supervised Classification with Graph Convolutional Network. It is one of the foundational papers on graph convolutions and mainly applying deep learning to graphs. And the authors are Thomas Kipf and Max Welling from University of Amsterdam. It's from 2016. I'm Parham Houni here as a research associate of Aggregate Intellect. We'll be presenting this. And we have Karim, who is from BMO, a data scientist at BMO. And then we will go through the details with you. Right now, I'm going through the overview of what would be the presentation about. So if you want to talk about the overview and what are the most important things in here, as you know, we discussed the CNNs and what they are and how we try to connect them to these graph networks. So the idea is that first of all, we see CNNs, then we go through why CNNs are powerful, and then we want to see that what is the difference between Euclidean data space and non-Euclidean data space, because we show that CNNs are applied only to Euclidean data space, and we need some modification in order to have it applied to non-Euclidean data space. Then we show how is it applied on CNN Euclidean data, and then we show by applying it to non-Euclidean data, which are graphs, we could have graph convolutional networks. And then we go deeper and show you why GCN works, why graph convolutional network works. And we go through some mathematical details in order to show you that the GCN works. Then, additionally, we show that GCN is quite similar to Weiss-Feidel-Lehmann algorithm, which is a graph isomorphism test and is one of the well-known graph isomorphism tests. And later, we go through the experiments and results, and finally we go through discussions. So, first of all, we say why CNNs are powerful. As you know, with the advancement and breakthroughs in deep learning from 2012 to 2016, as you can see, when deep learning has emerged, the accuracy rate in lots of high-dimensional learning problems had decreased tremendously. As you can see right now, they have reached some kind of accuracies which are even better than humans.
Increased or decreased?
Increased the accuracy and improved the losses. That's right. Yeah, right. Thanks. And now we want to see that, okay, what makes them so much powerful? The main assumption they have is that this is mainly based on the Euclidean data, and they are applied to grids, which are 2D grids and 1D grids, like images, which mainly they try to extract compositions from this data. So what I mean by that? For example, imagine that we have an image of a face, right? The image of a face can be, you can detect different compositions like eyes, nose, and these sort of things. And what we hope that our learner does, our CNN in here, is try to automatically abstract these features and extract them, actually. So the way we do it on Euclidean data, which is like 2D grids or 1D grids, as you can see on the right side, the difference between each, the distance between each node remain the same, right? That's the idea of the Euclidean data. But we go deeper as well and to show what's the difference between Euclidean one and non-Euclidean one. But the main important thing about this Euclidean data is that all CNN operations are well-defined and fast. So we want to extract these features. What we do, we actually make it by the convolution approach, convolution operation and also pooling operation. So if we want to say what are non-Euclidean data domain and how we can have it, and whether it's possible to apply CNNs and whether that's a question for us or not. First of all, you can see what are the important examples of graphs. You have seen it in most of the problems, like social networks, web, molecular representation, knowledge graphs. Mainly all the reasoning structure would be based on graphs. The applications can be having a recommender system, or the one that I'm working right now is on user geolocation, using interaction of people in social media and also their content. You can, for example, find their location through graphs and these sort of different techniques. So it's possible to solve multiple types of problems with this non-Euclidean data because they're mainly in that realm of data. So if you want to say more clearly what's the difference between Euclidean versus non-Euclidean data domain, in the main Euclidean data, it's like having a regular structure versus irregular structure. The Euclidean data domain doesn't have, the number of neighbors are mainly similar. They are well defined. But on graphs, for example, you have a node which has only one adjacent node, the other one has 10 adjacent nodes, so it can be different. And also there is no natural orientation of neighbors. So for example, in a grid, you expect that if it's in the middle of the grid, you expect that all over it would be like dots with same amount of distance. But in graphs, you cannot have such an idea. So that's the two key intuitional differences. But you can go into detail and find out more about mathematics as well, if you like. So if you want to show the convolution in graphs and see how they work, and want to somehow interpret this current CNN and architecture on graphs, this image would help you with that. So as you can see, on the left side, we have this normal convolutional filter that has been applied locally, and then we extracted some data from it. In the right side, we are depicting it as a graph. So you can see here, each pixel has become a node in our graph. And what we do by these arrows is we apply filters the way that convolution works. We apply weights. And then we add them all together. So you can see for H1 we have W1, for H2 we have W2, and so on and so forth. For H0 we have W0. And the end of the arrow points to the next layer in this representation. Okay, so what comes out of it would be the next layer in the CNN network. Okay? But if we want to apply that in graphs, that's the problem that we're going to face. We have multiple adjacent nodes, right? And the numbers are not set. So what filter we should apply? How much should be the length? What matrix? Do we have the dimension of that matrix? No, we don't. So what we should do, they have proposed a frame to somehow approximate it. The approximation is that we would have a single shared weight for all of the adjacent nodes. Instead of having W1 to W9, we only have W1 for the whole adjacent networks, as you can see in here, right? In here it shows that they share. And also for only the node itself, it's want to propagate to the second layer, we would have only W0. The only difference would be the difference between W0 and W1, which you can have as a hyperparameter yourself, right? You can change the ratio, so you can also say that, okay, I want to propagate the information from the node itself with a higher importance, right? For example, you have a social network and you want to consider the person and also its followers, or you want to consider the person himself more important rather than followers because he has more information about himself, right? So that's the way they have approximated the convolution in the graph domain, and then they applied this propagation rule to layer-wise to have this semi-supervised classification. So let's get deeper to it. Why GCN works? It is based on spectral graph clustering and based on spectral graph convolution. So let's define what's graph convolution. What's convolution in the graph domain, right? So the convolution is that applying a filter, which is g theta, to the signals that we have in the graph. And what we mean by signals in the graph, the signals in the graph are the node features. Just imagine them as node features, right? So what we mainly do in having a convolution is we apply a filter to this by the weights. The weights would be our filters. That's the whole idea. The weights that we apply in this convolutional network with the filter in here, the same understanding. So if you want to apply this filter in the graph domain, what you have to do is that you have apply it to a diagonal matrix.
I have a question.
Oh, okay. If you have a question, okay, that's fine.
Can you go back to the previous slide with the red arrows? Yeah, so W,
Or in
so
here.
the question is,
is W1 the weight for all the red arrows?
Yeah, exactly. They
Okay.
share this in the weight.
Okay. Cool. That's it. Thanks.
So now they're already interrupted. Have we still tackled the issue that it's non-Euclidean yet, or you're about to explain how we'll
Actually, we have approximated this function of convolution on Euclidean data, and we have approximated in non-Euclidean data. That's what we have done. Because if you want to go in, I would just in a few future slides I will show you.
Okay, great, thanks.
Okay. So that's exactly what we're trying to say in this slide, that right now we have applied the convolutional filter to the signal, right? And now, how we can apply it, in the graph spectral theory, it has been defined that when you want to apply a transformation, what you have to do is you have this analogous of the Fourier transform for the matrix of the matrix that represents the graph, right? So how do we represent the graph, first of all, and how do we represent the structure of the graph? The structure can be represented by the graph Laplacian. What's graph Laplacian? Graph Laplacian is simply the difference between degree matrix, the matrix that shows the number of adjacent nodes. For example, if you have a node that's connected to 5 other nodes, so the degree would be 5 for this node. And you have the matrix, diagonal matrix, suggesting which one has this, what are the degrees. And then you have A, which is the adjacency matrix, right? So the standard Laplacian is the difference between D and A. What we have in here is the normalized graph Laplacian. So this L is a graph Laplacian. It equals to the normalized matrix, which has been driven from D and A, D being the degree matrix and A being the adjacency matrix. And then they say if we do like SVD over this matrix, having the eigenvalues and eigenvectors of this matrix, the eigenvalues, lambda, would provide us with the Fourier basis. The Fourier basis is the base that you can apply the transformation in here, which is the filter, which is g theta. And why we do that? Because imagine that now you have this diagonal matrix, right? And then you apply this transform on it. So you just have to apply it to the diagonal points. So that would be much more efficient. And also there are some physical backgrounds that obviously we can't go into. So as you can see here, the g is applied to lambda. G theta is applied to lambda. And in graph spectral clustering, it has been showed that eigenvalues correspond to unique node embeddings. That is, we have had this structured, and then we have come up with numbers, which the numbers that showed the relationship of these nodes to one another. So if we want to see it through an example, in here you see the image. On the left side, you have the graph. The graph, as you can see, there's multiple number of nodes on it. And then on the right side, on the x-axis, we have the node row number. We have node ID. It starts from 1 and goes to 40. We have 40 nodes in this graph. And then for each of them, we have calculated this eigenvector, and eigenvalues actually, lambda. We have calculated lambda. And then we have assigned them to y-axis. So the y-axis shows that the number of lambdas for each of the nodes. So as you can see, the nodes that are in the same cluster, what we mean by clustered is that they are more connected to each other and less connected to other parts of graph. So as you can see here, for example, we have a cluster in here, another cluster in here. As you can see here, these clusters on the left would correspond to numbers in the right, which are easily, for example, by k-means or other type of algorithm can be separable. So we have this unstructured graph, and then we have made it in the embedding, and then we could successfully cluster it. Yet this idea is, the problem with it is computation expensive, because the multiplication with the eigenvectors and calculation of eigenvectors is N2 is a polynomial. So the problem arises to how to reduce this computational cost. So if we want to do such a thing, I guess Karim has a question. But we can't hear you, Karim. Yeah, everyone, if you can, you have question, you can put a comment, please, on the live chat.
Can you speak again?
Yes, yes.
We can now.
Okay, can you go back to the previous slide, please?
This one?
Yes. So
Yeah, we,
for the plot
this is he says that the values on the y-axis, is this the way that we clustered the nodes? No, it's the node embedding. What we mean that is the value for the eigenvalue. Is it the eigenvalue? For example, the eigenvalue for node 20 would be around something around minus 0.1 and minus 0.75, something like that. You see, this. So we were just saying that, to wrap it up again, so we have this computationally expensive, mathematically proven method for calculating, for clustering the graph. But the problem is that if you want to, the problem is if you want to have this calculation, it would be quite expensive. So what we have done is that we have tried to use Chebyshev polynomials in order to approximate this calculation. So as you can see here, the Chebyshev polynomials, which has been first introduced by Hammond in 2011, the network is called ChebNet. It tries to, as you can see on the left side, it tries to define the convolution by having a theta prime, which is a Chebyshev coefficient. It works the same as our weights in the graph and convolution networks that I showed. This is the weights. And also with TK is a recursive Chebyshev function. So if you remember your calculus, you can come up with what's more Chebyshevs. And then in here, the L tilde would be an approximation of L, which is the graph Laplacian. And Y max is the maximum value of the eigenvalues, the maximum value of eigenvalues. So they have proposed it, and it has somehow improved the computational cost. Now GCNs are approximations of ChebNet. It's two-layer of approximation and relaxing the assumptions. So what GCN has done is that they have said they have fixed y lambda max to 2, and then they have only used expanded the Chebyshev polynomials into order 2. So you can see we have this theta prime 0 and theta prime 1, only these two. And then they have come up with this Chebyshev approximation, and then what in here they do is mainly just doing some linear, doing some algebra and calculus to somehow wrap it up. And then they have this real problem. If they want to do this, calculate this value iteratively, the problem would be that maybe because the lambda max is set to 2, maybe it could have numerical instabilities. So that's why they have used a normalization trick and then approximated the value in the middle part, which is in plus d minus power of half and so on. They have replaced it with an approximation. And what is the approximation? The approximation is that instead of A, you have A tilde, which is the value of A, the adjacency matrix, plus the I value. The I is the unit matrix. And why is that? Because it's like having this self loops in the slides that I showed you earlier. One weight for the all. And what they do in here is they essentially provide, they think that W0 and W1 are the same. They don't differentiate between them two. The lambda that we define is in here equal to 1. Okay? Now the complexity becomes smaller, and it's now in the power of E, F, and C. And what we mean by E is the linear in the number of edges, F is the number of filters that we want to apply, and C is the dimensional feature vector for every node. So how, for example, what is the dimension that we want to embed into, right? So let's revisit it again and see what we were talking about. So we showed you this huge matrix. This huge matrix, an equation, what it had was essentially this slide. We have this W0 and W1, which were theta in here with theta, capital theta in here in the slide, as you can see. And then we have, you see this 1 over C. This is the approximation. This is normalizing over the number of adjacent nodes. In here, it has been done by this operation of multiplying d into power of half, minus half, and a, and d power of minus half. So this is essentially the mathematical proof that where this propagation rule comes from. Okay? So if we want to apply this framework to a problem, how we can apply it? The assumption, the inputs can be a graph which we have some labeled data and some unlabeled data, and the output is a predicted node label of unlabeled data, right? So imagine you have a social network that some of people interacting with each other, and you have some information about the people who have interacted with one another, and you don't have any information of some others. You have two friends, one of them you know information about, the other friend you don't know nothing about. And that's the whole idea, to find out, okay, whether I can get some information about the friend that I don't know nothing about. And the output is, as I told you, the predicted node label. And now we have earlier approaches which were based on embedding-based approaches. So what is that? We have this, we embedded each node to a numerical Euclidean space, and then when we have done it, then we trained the classifier on them. We didn't see what was in the node features. We didn't have any idea about node features. We just took the adjacency matrix or graph Laplacian and that sort of things, and then we embedded it without having any interaction with the X, which is the matrix of node features, and we just had this embedding. Then we concatenated them, or that sort of approaches, like node to vec, like these sort of ideas. But with GCN, the good thing is that the training would be end-to-end. That is, you take the graph structure and also node features all together. You train a model end-to-end. You don't have to do a process for node embedding and another process for feature extraction and then combining these two for concatenation together. Sorry. Okay, so the overview, as I told you, is that stacking 2 layers of this convolution together, essentially, and then adding a nonlinearity in here is ReLU, and then at last having a softmax. So what it does is the function of x simultaneous. Like we have a machine which has as a function of x, the node features, and also a, the adjacency matrix in here, right? And then they have used this propagation rule, and they have used only 2 layers, not more, and we can discuss the details why. And then they have devised this loss function, which is, we have this over the right. Okay, so even if we don't have any good information on the nodes, I mean, the node features are quite completely random, then we can even get meaningful clusterings with GCN. So how is that? So, as you can see on the right side, we have a graph, and we have initiated all of them with random numbers. So the x that corresponds to each node is a random number, right? So what we want to do is we want to train the network based on this GCN that we have. So as you can see here, they start from 0, and then after 200 epochs, they go to this meaningful representation. You see that the node labels, which are closer together in the right side in the graph, and they're more connected together, are actually clustered together in the representation that we have on the left side, right? So it even shows with this kind of framework, even when you don't have a good thing, then I guess Karim with a question again.
Oh, Karim has a question? Sorry.
I guess if you have it on chat, it's better because of the noise things. Can you type it, Karim?
Can you unmute yourself?
I can mute Karim.
No, sorry. Do you have a line?
I can mute.
Karim, can you speak?
I
You
asked the
can say
question
now.
with YouTube channel.
Okay. So the question is, are we seeing a two-dimensional embedding of each node in the left block?
Are we seeing a...
We can have a representation in two dimensions or any dimensions that we want. So we have to first get to, it depends on how we want to, it's our design actually, you know, because it's a number of layers and that's what we have, so we can design it the way we want it.
So I think the question was though, is it a two-dimensional embedding on the left side? And I think the answer is yes, right?
Yeah, on the right
left
side,
side.
yeah. But I'm thinking maybe it should be necessary two-dimensional or not.
It can be.
Another question. Can we say that nodes which are closer are similar words, for example, in the social network example you gave?
In the social network, for example, it can be friends who are interacting with one another, you know. Because on the words, you have to go through NLP models, you know, just completely different area. Because the way you define context in the words is different from here. In here we have this graph. In social network, the idea is we have this graph of people interacting with each other, right? So they have friendship or not, right? Okay. So, additionally, we have other proof for GCN as well, which is the Weiss-Feiler-Lehman graph isomorphism test. What is that? It's essentially that it has been an algorithm developed in 1960s, 1968 to be exact. And the difference is that this test is a popular test which has been proven and it's been used to test whether two graphs are identical, similar, or not. The isomorphism shows whether and it's used, for example, to check that whether two molecules are similar or not, something like that. And the difference that GCN has with this Weiss-Feiler-Lehman algorithm is that instead of the hash function that it defines over there, we are changing it with this GCN kernel that we have provided, which is possible that we do a backpropagation rather than a hash function, so we can train the network. You know, that's the good part that GCN has. But it also relaxes the hashing assumptions that it may, for example, provide some other stuff as well. So, what are the experiments that we had? They had actually. They had 4 experiments on 4 benchmark data sets. 3 of them are citation networks, that is the network of people who have cited one another in the academic papers. And the other one is a knowledge graph. This knowledge graph also has edge features and also direction. The rest of the citation networks are undirected graphs and unweighted graphs, but knowledge graph of ours is weighted and directed. So they have used this 2-layer framework, only applying 2 convolutional layers, graph convolutional layers, as it's seen in the down. And then they have tested with multiple powerful baselines at that time, at 2016. So they have shown that GCN is both provides better answers with higher accuracy and also in shorter amount of time. For example, they have used this node embeddings, not debug, or other approximation of graph spectral learning, or used, for example, DLP. What it does is essentially it provides like a regularizer over the graph representation, which is like matrix of A or matrix of D or something like that. But right now, they are not, even GCN is not the state of the art. It's one of the foundational, so I won't go deeper into that. And so what they have done is that they have reached these good results, but they had some limitations which other newer papers have tried to solve. For example, they had this problem of memory requirements, because with this kernel, it's not possible to batch, because each time you have to find out exactly how many nodes are connected to one another, and the adjacency matrix is invariant to change. You can change the position of rows, and it won't make any change in the graph structure, but will make difference in your graph, in your, matrix, adjacency matrix, right? And the other thing is that it doesn't get into account directed digits and edge features. And the final thing is that they had this limiting assumption that all of the, first of all of the nodes that are this node itself and all the adjacent nodes have the same similar weight. But in here, as I showed you earlier, with providing lambda, they try to differentiate between the node itself and other nodes.
Question.
Sure.
Could you elaborate why is it difficult to batch the first one? Repeat the question.
And they say it's difficult to batch. Why is difficult to batch? Okay. The answer comes from, imagine that you want to batch over the network, right? So what it shows essentially is that you have this diagonal A, not diagonal, this square A matrix, right? So what it shows that which node is connected to what other node. So if you take 10 rows from top, it may show connection from what place from the, for example, node of 168, and you don't have it in your batch, right? And you don't have the information in your batch. So if you batch it, what you will have is you are sampling from the data, and yet you are not admitting that you're sampling from the data. You know, that's the batching thing. Because you're sampling with a framework, but you are not sure how it's because some of the parts of the data which are labeled, for example, more than their batch size will be deleted. You don't have the information coming to your system. There are other sampling methods which are more robust, like GraphSage or other type of networks that we can go deeper if you like.
That could be a future presentation.
Sure, definitely, future presentation. Okay, any other questions? And then we go to, by the way, let's wrap it up. We go to key takeaways of this presentation. We showed that graph and non-Euclidean domain needs special consideration to apply deep learning success like CNNs. And the GCN, which is one of these kind of networks, has mathematical explanations as proven to be powerful in both application and theory. And it's one of the most successful algorithms in deep learning on graphs, which has resulted in multiple ways for research. So as you can see, there are lots of research based on this network. And you can see there are, I guess, more than 800 citations for this paper. So it shows the impact of this paper and how it's helped the graph networks. And so we also have a discussion points. If there are people who could contribute, that would be awesome. If not, I will go through them and let you know about it.
Let's go through the discussion points. People feel free to ask any questions, or if you have any clarification questions, argumentative or comparative, feel free to ask.
Okay, so the discussion points, one of them was, why not more layers? We say it's deep network, but we only use 2 layers. Why using only 2 layers? The question can be answered intuitively by saying that imagine that you are trying to model a social network, right? You're trying to find out information about a person while gathering information about the people who are connected to him in a friendship or other type of social context. So imagine that you want to get the information from person A, and there are 5 persons who are his close friends, and then there are other people who are friends with the close friends, right? So if you take more than 2 layers, what you're essentially doing is getting information from friends of friends of friends, you know? It's become more like a noise rather than becoming an information. So you're gathering information which are irrelevant to the node itself, right? So that's, you are somehow you are messing up with the locality of the data and getting information from all over the graph. So it's not a good way to capture compositionality. And the other question is, why spectral graph clustering uses graph Laplacian matrix? Okay, we said that if we get these eigenvectors and eigenvalues, this would assign to a unique node embedding. Do we have any proof for that? Yes, we do, but it will take some time. I will make other questions first, but if we have time, I will go through that. And the other thing is how to make GCNs scalable to big data, the problem of batching, right? One of them is accept that you have this not best way of sampling without any rules, sampling way. The other one is using GraphSage or other type of methods which have sampling like unified sampling methods, they declare what is their sampling method. And this is mainly the best choice. And the fourth question is, how is it different from gated graph neural networks? Essentially, it's quite the same because they are in the same year. The only difference is this gated mechanism that they want to also apply some weights, somehow tweak with the weights, but it's essentially the same. And
How is it computationally different from gated graph neural nets?
well, actually, I'm not sure about that. I have to check it.
Could you repeat the question?
He asked how is it. He asked how is it different with the difference between gated graph neural networks and graph convolution networks in terms of computational costs. And I was like, I'm not sure about it. I have to check and let you know through comments. And the fifth discussion point is what are the differences between this framework and other networks such as graph attention networks that Karim, I guess, will be presenting soon, which are like more state of the art. What are the differences and how they could improve that, whether we have any idea or not. That would be a good point.
I'm just insert advertisement here. I think April 15th we will have another talk by Kareem on graph attention networks.
Exactly. Yeah. Just check that out as well. Yeah, just check that out. Yeah. And if you have, do we have time? Do we have time? Okay. Yeah. So let's talk about, it's like a bonus part, an appendix type. Let's talk about why spectral graph clustering using graph Laplacian matrix, whether it has some intuitive and also some mathematical proofs behind it.
How long do you need for that part? 10 minutes? Okay.
So, if we want to see what we did by spectral graph clustering, it was 3 basic stages. We had this pre-processing, we had this matrix, we got this graph represented by matrix A, D. We try to capture the information of the structure of the graph by these matrices, right? Then we try to decompose it, compute the eigenvalues and eigenvectors of the matrix. Then we try to map each point to a lower dimensional representation based on one or more eigenvectors. Okay? We had these eigenvalues. If we multiply eigenvalues by eigenvectors in a k order, we would have the dimensions that we want. Okay? And then we group them based on the new lower dimensional representation that we had. Okay? That was the whole procedure, right? But in here, we want to say, okay, this lambda 2 is one of the eigenvalues. So how we could say, it's already proven, it's, I guess, right equation. I'm not sure, I should check that. It's proven that we can take this equation as true, that lambda 2 would equal, when you have a matrix, it would do the minimization of SVD of this matrix and over the multiplication of the matrix, okay? So if we try to open it up for the graph Laplacian, what we have in here, down there essentially, is that we just replace the values and we open that with summations. And then we replace L with D and A, which is its definition. And then, since D is diagonal, we said that, okay, it can be a summation over the diagonal parts and x. And then minus ixj is the nodes that are connected. I and j are a set of nodes that are connected to one another. Okay, so E is a set of all edges in here, right? So they have also used this dixi2 as saying that, okay, we want to go through, they have just expanded it by the same definition and said that, okay, we can say that it's xi2 plus xj2 minus 2xi, which is a simple equation. So what it's essentially getting, this eigenvalue lambda 2, what it's essentially calculating is the difference between the variance between each point in the point in the node features, right? That are connected to each other. That's the only assumption that we have. So we have also two other assumptions. that because x, we want to set x as a unique vector, and also we want it to be orthogonal to 1 eigenvector. So by having this two, we would get this minimization as having two constraints, and by that, we should see that, okay, we have assigned this graph to this place. Well, we have this, we have a node A1 and node 2, and we have set one of them over 0 or some of them below 0, because the summation should be equal to 0, and the squares, the sum of squares should be equal to 1, right? You see here we have these two assumptions, and then we want to minimize the difference of the distances between the two. So for example, we have xi on the left side and xj on the right side. So we want to minimize the distance. So we want to make it closer to each other. But the problem is we are constrained. We're constrained to the fact that one of them should be over 0, the other one should be below 0, right? And the other thing is that the value should, the square should equal to some. Okay, Karim, you got me? I guess Karim is a little confused. You okay? Okay, good. And then it shows that we can do this clustering for only two. We just did by partitioning mainly. That's a better way to say it. We just partitioned the graph in two partitions. So how about if you want to do a multiple partitioning? There are two ideas about it. One of them is recursive by partitioning. That is applying this algorithm recursively, so we could have other multiple partitions. But it's inefficient and unstable. The other one is using multiple eigenvectors. Rather than having eigenvalues only, we could get the eigenvectors, because we can have this, build a reduced space from multiple eigenvectors and multiply it by eigenvalues, and which is a preferable approach and has been done. But the main problem with that, as I told you earlier, is the problem of computational cost. Okay? I guess that was it from me.
So there are a couple of comments and questions.
Right.
So one, Karim has mentioned regarding batching.
Right.
One second. Regarding batching, wouldn't it be possible to use graph partitioning algorithm that minimizes the number of edges across clusters to first renumber the nodes? You did also talk about partitioning here, but I wonder if you have addressed this yet.
So the
Then doing batching, we can include each batch, the nodes in one cluster and their neighbors.
Well, the question arises how you want to. You can easily change the location of the graph, right? Of the nodes, right? The question is that it is the problem we have with Euclidean data is that we can easily move them, and the distances doesn't make any sense for us, right? But we get the understanding of distance from the connections that they have. We do the, so if imagine in here, let me show it here. This one, if you look at it, you see on the left side we have this structure of data. But on the right side, imagine that if we change the location of one node, okay, we put it, we like drag and drop it, imagine that we stretch it all over the place. It doesn't change the structure and the connection of the networks, but it may seem like, oh, it's far away, it's not connected to the same cluster, right? So we have to have a systematic way to be sure that, okay, it's not dependent on our node labeling, you see? Because if you want to check it visually, then it's problem, okay, whether it's connected or not. We want to have this algorithm which is not related to our way of putting the node numbers, assigning values to nodes. Assigning IDs to nodes, yeah, that's a better way to say it.
Okay, there is also another question from Iggy online. He's asking, the challenge is transforming non-Euclidean to something we can work with. I think graph Laplacian provides one linearization method, wondering if there are others.
Yeah, definitely sure there are others. For example, I mean, the way that GCN tries to capture the clustering, or can you rewrite it? Question again?
So question is, you seem to be using Laplacian to transform graph into, like to linearize the graph into some numeric representation. And they were wondering if there are other ways than Laplacian.
Well, that's basically doing the node embedding, right? We want to have this graph and then we want to do a node embedding. There are other type of frameworks which are based on, their approximations, but they're based on the successes of NLP through word2vec or doc2vec or that sort of things. They have applied it to the graph domain and they have reached to models like deepvec and node2vec, which are like the prominent models that you, simply the idea is that you scan the network structure based on as having like a context of words. You scan it and then you get the information and then you do, but with skipgram you do a like pooling and aggregation function. That's the whole idea. But they are not as accurate in terms of mathematical proofs as this one. This one is essentially the main one. The other ones are approximations, how you go through the graph. That's the idea. How you walk.
All right. Great. We have about less than 5 minutes left. If there are any other questions. All right, great.
Thank you.
Thank you very much.
Thank you all. Thank you. It was a great pleasure to meet you.
Thanks, Param, and thanks to Kareem for facilitating. Thank you, everyone. See you next time or on Wednesday.
Also, thank you.